configure and share screen. Here we go. Okay, so starting the class today. And there's nothing special about logistics this week. So again, if you would like to have some subjects discussed in discussion section on Thursday, do let me know. If you have any ideas right now, please tell me.
I think I'll probably end up having questions on that second question on the homework.
Okay.
I haven't looked too deeply into it yet, but hopefully I'll have time to work on it before. I think in particular, I was a little bit confused by the notation of that that line integral defined on this lattice.
Okay.
So I could bring it up then.
All right, so I would definitely discuss that. Anything else?
Can you talk about CFT?
I can, yeah, it's a big subject, but I can touch on it. Yes, I would be happy to do that, yeah. Anything else? Somebody left? Okay, so let's then, oh, go ahead.
Could you please expound a little on the correspondence between terminologies mathematicians use and physicists use?
So kind of dictionary.
Yeah.
In gauge theory, eyeball. Is that what you meant? Okay, anything else? Is it good? Okay, so let us get started with the continuing the quantization non-abelian gauge series. So we found a way of writing down a gauge invariant Lagrangian. So here is one example. So I have a fermion field, and just like what Nick was asking a few minutes ago, so psi is meant to be some n column vector, and each component is a Dirac fermion of its own. So there are actually 4 times n components in psi. And del mu is acting on a space-time index of psi, statement argument of psi. A mu is acting on this n by n pieces. And this gamma mu is acting on this 4 by 4 spinor indices. So it's a fairly big Lagrangian, even though the notation is pretty compact. And mass term and the field strength, and that provides a kinetic term for the gauge field. And the F mu nu, as we just talked about together with Mario before we started, can be written down explicitly this way. So if you look at the square of F mu nu, then I have a cross term between this curl and this A mu A nu, and that's cubic in the field. So that gives you this Feynman vertex. And it actually has several terms in it. And the reason why there is a momentum dependence of this vertex is because each of these derivative would turn into a momentum in the momentum space. So that's a new vertex we didn't have in QED, and that's strictly there because of the non-abelian nature. And indeed, it's proportional to the structure constant that indicates that has to do with the commutator. And this square p squared gives you quadratic term in the field, so there's a 4-point interaction because of that. Again, there are quite a few terms in it, and they all come with the structure constant squared because we're squaring this term here. So these two, the vertices are brand new in non-abelian gauge theory. But the way you derive it is completely straightforward, just like what we have done with the scalar field theory and the QED. You just take this interaction Lagrangian, take it down from the exponent in the path integral, use the Ewig theorem to work this out. So, so I don't think I need to explain anything more about this. So it turns out to develop perturbation theory, it's actually a little bit more tricky to talk about propagator, which is kind of surprising. So in the case of QED, this is actually copied from the Peskin-Schroeder. So we have this vertex of minus I gamma mu. We have the photon propagator minus I g mu nu over q squared. And then this talks about these polarization vectors for the external photon lines. So that's what you were told last semester, and you develop perturbation theory with it. But the question is, how do we get this? So certainly, in order to develop perturbation theory, we need vertices and propagators. And the propagators, as we learn over time from the path integral formulation, they are inverse of the quadratic term, the Lagrangian, when you perform a Gaussian integral. And so in the case of QED, the quadratic term for the photon field is just F mu nu. And if I take the F mu nu explicitly as a curl, the curl times curl, you are summing the mu nu indices antisymmetrically, so I can save one of the combination by changing 1/4 to 1/2. Then if I do the integration by parts to let this positive derivative act on this side, then I can rewrite the Lagrangian this way. And try to take the inverse of this. I go to momentum space, and so box turns into negative q squared. The derivative turns into iq mu. So the thing in the parentheses turns into q squared g mu nu minus 2 mu q nu over minus sign I left out. And the question is whether I can invert this matrix in the mu nu space. That's a 4x4 matrix. But it turns out you cannot because there is a null vector. So if I multiply this matrix on q nu vector, then the first term becomes q squared times q mu, because there's some of a nu in this. And the second term becomes q mu times q squared. So q squared q mu minus q mu q squared vanishes. So there is actually a vector with a 0 eigenvalue. And therefore, this is not invertible. Therefore, you cannot actually work out the propagator. So when you actually use this propagator last semester, the natural question is, where did it come from? And Peschke-Schroeder is, I believe, intentionally very vague about this. So they just give you this as a propagator and tell you to use it, but it doesn't talk about how they got it. And so they've been hiding behind this fact that when you think about the Klein-Gordon propagator, that's I over q squared minus m squared. So talking about massless propagator as 1 over q squared sounds natural. And being a vector field, putting g mu nu to be consistent with Lorentz covariance is kind of natural. So it looks reasonable, but the question is, how do we get this? So that's the question we have to talk about, which has to do with the gauge fixing. Anyway, any questions on this slide? Okay. So what should have been done is this. So when you actually deal with the QED Lagrangian, so before going to non-abelian gauge theory, we got this F mu nu term. And let's say you try to take some kind of Lorentz gauge. But because we're dealing with a quantum system, we impose this Lorentz gauge condition as the quantum average. So this is the Gaussian weight you assign to del mu a mu, so that at the minimum of quote-unquote potential energy, del mu a mu vanishes, but it can fluctuate around it. So that's the term I'm now adding to the Lagrangian. And we make it even more formal how we can actually obtain this term in the Lagrangian later on. But just take it for now that this is what you add to the Lagrangian, and that's the way gauge fixing is supposed to be done. And once you actually accept that, I can further rewrite this term, again using partial the integration by parts, so that by combining it with the F mu nu term, we had box g mu nu minus del nu, that's this 1 in here. But this new term gives you this 1 over c. So if you put both of them together and go to momentum space, I have this combination, g mu nu minus 1 minus c times q mu over q squared. This actually is invertible. So if you take the Feynman gauge, when c is 1, and that's the gauge the Peschke-Schroeder encouraged you to take actually without telling you, then this piece just vanishes, and g mu nu has an inverse, that's g mu nu itself. So this is the propagator you actually used, which secretly relied on taking c equal 1 together with this gauge fixing term. So as I said already, so this term is meant to give you this Lorentz gauge condition on average with a Gaussian weight. There is a formal limit you can take when c goes to 0. Then this potential energy, so to speak, becomes infinitely steep. So that's the limit where c mu, del mu a mu is strictly enforced to vanish. And so it's a little tricky to take C going to 0 when it involves actually inverse C. But after taking the inverse of this quadratic term, the propagator now has C in it, not C inverse. So you can take C going to 0 limit. And that is what is called the Landau gauge. And then your propagator looks like this. And then of course, that brings up an actual question. Are we sure that physics doesn't depend on this parameter C, because this is meant to be a parameter that is just associated with a gauge fixing procedure, nothing physical about it. So anything physical, all scattering amplitudes, should not depend on this parameter C. So there are two questions here. So how did we end up with this additional term, the Lagrangian, to begin with? We have to justify that. And second, do we know that the physics is still invariant under the gauge transformation or change of parameter, gauge fixing parameter C? So these are the things we need to understand. So in retrospect, this is what you have actually done secretly in part 1 of Peskin Schroeder without being told. But now we have to understand this once and for all. So that's the question we need to discuss. Any questions about this slide?
I have a quick question. So I would think of gauge invariance or gauge fixing as depending on an entire function, because we have the freedom to add the gradient of an entire function to a mu. Mm-hmm. So why do we boil down gauge fixing to a single number C if it's supposed to depend on the entire function?
Yeah, that's an excellent question. So right now I can't answer this. Hopefully that becomes clear once we go through the discussions and remember to ask the question again. Okay.
Okay.
All right. Any other questions here? Good. And so when you actually try to do the same thing with non-abelian gauge theory, Feynman actually tried to do this. So without going through every single step of what exactly is the gauge fixing procedure, he just forged ahead to do perturbation theory for non-abelian gauge theories using that propagator we just talked about. And then he discovered a pathology with it. So he discovered that it violates unitarity. So unitarity tells you, this is the optical theorem in quantum mechanics, so imaginary part of the scattering amplitude in the forward direction is supposed to give you a total cross-section. And so, from the point of view of Feynman diagram, what that means is that if we have a Feynman diagram like this one, taking imaginary part is actually taking this I epsilon prescription for the loop integral, which cuts this diagram in halves and open this up so that this internal line becomes an external line. And this one and that one accomplish conjugate to each other, so that actually turns into the square, absolute square of this the Feynman diagram, and they're supposed to be equal. That's the consequence of unitarity. But when Feynman actually forged ahead and did the calculation explicitly and checked whether this relation is satisfied, it was not. And of course, that was a huge problem, because when unitarity is violated, then of course the probability is no longer conserved and everything about quantum mechanics goes haywire. So that shouldn't have happened. And so something is wrong with this. And then Feynman couldn't figure this out himself, but it turned out that when he actually forced ahead into perturbation theory, he assumed just a standard propagator, standard vertex, and didn't worry about how to actually exactly do gauge fixing. So he was sloppy about it. So in order to avoid this problem with unitarity, we really are actually forced to go through every single step on what we think is the gauge fixing procedure. So that also has to do with the question on previous slide, how exactly we justify the propagator, how do we introduce this gauge fixing parameter, and that is now forced upon us. There's no way out, because we have to save unitarity to make sure that quantum theory is consistent. So this is yet another reason why we have to go through every single step of gauge fixing. Any questions about this? All right. So this is now our view of the gauge fixing. And it's actually sort of a geometrical, because we formulate now gauge theory in terms of path integral. So the question is, can we actually divide up or decompose this integration volume over all possible gauge fields into two pieces? So what we call a parallel is the direction that corresponds to gauge transformation. So it's parallel to the gauge transformation. So let's suppose you have one slice here, which corresponds to Lorentz gauge del mu a mu vanishing. But there's next slice, which corresponds to different gauge. So I change the gauge of a mu to a mu minus del mu theta 1. So theta 1 is a gauge parameter. So on this slice, gauge field satisfies this condition. Next slice, it satisfies slightly yet another different condition, and so on and so forth. So these theta 1, theta 2, theta 3, theta 4, and all these are just different choices of the gauges you can take. And so you have these different, what we call gauge slices in this big space of integral over all possible gauge fields. A perp corresponds to the horizontal direction in this cartoon. So each point on this gauge slice with different value of the A perp corresponds to a physically different gauge field configuration. On the other hand, in a vertical direction, if I start from here to jump to next slice and next slice, I can draw a line, and I think I can draw a line, draw line like this. So every point intersection of this line on gauge slice corresponds to the same physics. So the original integral we had on the all possible gauge fields actually correspond to a very redundant integral, namely that I'm summing over the same physics many, many times over. In fact, infinite times. So the idea of gauge fixing is that, well, we're not actually, we don't have to do this integral over A parallel because I'm just summing over the same thing over and over again. So it would be great if I can just drop this integral over A parallel and just do the integral over A perp to sum over physically inequivalent gauge field configuration. So that's the idea of the gauge fixing. So we choose a gauge slice, whichever you like, and just do the integral on that slice only. And so we don't do the integral over A parallel anymore. We just do the integral over A perp. So that would be the most economical thing to do. So the idea is that if you stick in this delta function of the delta A mu minus del mu theta to vanish, so this delta function or delta functional corresponds to the restriction of the original integral down to one of these gauge slices. And if you're allowed to do that, then this piece or the integral over A parallel is now gone because you restrict yourself to be only on one of the slices, and you have integral only on A perp. Once you have that, then you should be able to invert the kinetic term and then define the propagator. So that would be sort of the ideal thing to do, but the question is this correct? I sticked in this delta function by hand, and it looks reasonable, but is it actually justified? So what I need to make sure is that after sticking in this delta function, the result without delta function and the result with delta function are supposed to be the same only up to a oval coefficient, which counts the number of slices you have in the system, right? So that's the idea. Is that really true? So it turns out that in the case of QED, it is true, and we are allowed to do this. But when you go to non-abelian gauge theory, if you remember the infinitesimal gauge transformation from going to A mu, let's say U1, that's a small gauge transformation I have done from here to there. The gauge transformation itself depends on the gauge field, right? So this is how much infinitesimal gauge transformation changes the gauge field. This is the original one A mu, this is a new one A prime mu, and difference depends on this derivative of the gauge parameter, just like in the abelian case. But this is yet another piece that involves the gauge field itself. Namely that distance between one gauge slice and another gauge slice depends on where you are in the horizontal direction. That depends on A perp. So if that's the case, when you try to restrict your integral to one of the slices, you can make a mistake because in some sense here the gauge slice is supposed to be thicker and here is thinner because the distances between these gauge slices now vary along this horizontal direction. So you have to actually take care of the fact that here, this distance is bigger, and therefore this should carry more weight. And here is thinner, so this should carry less weight. So you have to have some factor that depends on where you are on the gauge slice. And that's the thing you didn't have to worry about for abelian gauge theory, because the gauge transformation doesn't depend on a mu, but you do have to worry about it for non-abelian gauge theory. So that actually turns out the major difference between abelian gauge theory and non-abelian gauge theory. And that is what has to do with what is called Faddeev-Popov determinant, which you might have seen in Pishkin-Schroeder already. So that's the conceptual issue here. So how do we figure out sort of this issue of this distances among the gauge slices so that you can make sure sticking in delta function would not change the result of the path integral? So I will make everything more explicit as we go on, but any question about this at the conceptual level?
So just to be clear about the interpretation of the lower picture, so it still turns out to be the case that every gauge condition has the same measure, right? But now the local volume element depends on the physical part of the field.
Right.
Okay, so the bottom picture where like the purple one is actually bigger area than the blue one, that's not really what.
Yeah, that's not what it's meant to indicate.
Okay.
Yeah, this is just a cartoon, so I couldn't do better than this.
No, yeah, it makes sense. I just wanted to.
Right.
Okay, thank you.
So the Mario's question is that whatever we can integrate over this purple slice, what we can do on this orange slice and the light blue slice, they're supposed to be the same thing. So just like the previous case of abelian gauge theory, when you go along this direction, then we are summing over the same physics over and over again. So it doesn't make sense to restrict the integral down to only one slice. But when you do so, you have to be a bit more careful, because how much the distance there is between the gauge slices now depends on where you are on this one particular slice, and that's something we need to figure out. Yep. So thank you for asking the question, Mario. Any other questions here? Okay. So in order to understand this issue, we now back down to something very simple. It's not field theory. It's not path integral. It's just a regular integral. And it's two-dimensional integral as a first example. So this integral over x and y plane has a weight which depends only on the distance from the origin r. So this integrand is rotationally invariant. So this is just one example of that. But because it's a rotationally invariant, we can make the following argument. Well, so we are summing over the same thing over and over again along this azimuthal direction. So let's just put one slice and integrate over that slice only. Then we don't have to do this wasteful integral of summing over all these azimuthal directions. I just take one slice and be done with it. So let's say this slice corresponds to the plane y equals 0 on this xy plane. So then I stick in this delta function of y to restrict my integral to this plane. And then I can immediately perform a y integral. Then I find this is dx e to the minus s of r, where r now becomes absolute value of x. So this should be right? But it's actually wrong. And you know that because what you can do is to first switch to the polar coordinate. And then this dx dy turns into dr d theta. And nothing in the integrand depends on theta. So d theta integral can be performed right away. And it's just a constant 2 pi. And so if I take this attitude that I don't care about over normalization of this integral, that's what we always do in path integral, this 2 pi is nothing we care about. So I can write this r integral now as an integral over absolute value of x. And then this is the final form, which is definitely different from this very naive argument I made by sticking in the delta function of y. So what's different here is this factor of absolute value of x, which is missing here. And this is precisely what I meant by the distance between gauge slices. So here there's one slice, but let's take you have another slice which is slightly angled relative to the original one. And then you ask the question, is the distance between two gauge slices uniform along the slice? And it's not, because as you go along this slice away and farther and farther away from the origin, the next slice becomes more and more distance from this slice. So distance grows with x. And that's exactly the factor of x I have to stick in to make sure that integral doesn't change after choosing one particular this angular slice. So that's precisely what we need to know. Namely, is there any kind of sort of a Jacobian by doing the change of variable from original Cartesian coordinate to polar coordinates? And when you go to this polar coordinates, you have this Jacobian factor of r, which we need to keep to make sure that integral doesn't change. But naively sticking in this gauge condition gives you a wrong answer, because the distance between different gauge slices now change as you go along the gauge slice, and that precisely is this factor x in this particular case. So we need to generalize this discussion into more general symmetries, and in the end, we go back to the gauge symmetry. So this is what we need to figure out, and that turns out to be what people call the Faddeev-Popov determinant. Okay, any questions about this simple example? I hope this makes sense. And there's the lecture notes I posted on B courses, fp.pdf, Faddeev-Popov.pdf. And obviously Faddeev-Popov are the people who first came up with this idea of trying to work out this kind of Jacobian correctly. And hence it's called the Faddeev-Popov method. No questions? Okay, so then let me move on to the next slide. So what is the right thing to do then? So the first thing we need to figure out is what is the meaning of the delta function of function. So when you think about delta of f of x, and in the end, of course, we will be talking about delta of divergence A to enforce the Lorentz gauge condition. So the argument of delta function in general is actually a function of function. So that's why we need to actually understand how that works for now. So here I have just one example of such a function, f of x. And the basic idea is just to use the chain rule. So if you integrate delta of f over f itself, then by definition, this is 1. And then we change the variable from f to x. So df now becomes dx times df by dx. And so this is the Jacobian of the change of variable. So because this is just a change of the variable, this is also supposed to be 1. So namely, delta of f of x has to be accompanied by this Jacobian df by dx. So that's the basic lesson we learn out of that. But we also need to be a little bit more careful, because this df by dx is positive here around this 0, but it's negative here and positive here again. So when you literally do this integral, I end up summing 3 pieces where argument of delta function vanishes. Here I get positive contribution. Here I get negative contribution. Here I get positive contribution. So in this case, it's okay because I have 2 positives and 1 negative. So it still gives you a finite answer at the end of the day. But if I had a function like parabolic function, which had only 2 zeros, then I get negative and positive, which cancel against each other. So I end up getting 0. So that's not what we want. So instead, we put the absolute value for this Jacobian so that each 0 contributes with the same sign. So in this case, this ends up being 3. So if you do this integral with a delta function of a function together with Jacobian with the absolute value on it, this ends up being the number of zeros of this function. So this is the general statement for arbitrary function f of x. So if you want to stick in delta function of some gauge condition f of x, then first of all, you need to take care of this Jacobian factor, otherwise you get a wrong answer. But in addition, you need to make sure that this Jacobian comes with absolute value. And then you can stick in this identity that integral over x together with this integrand just gives you a number. So then we are justified to do the following. So in the case of this rotation, so let's say I start with the position XY on this plane, and then this purple point is a rotated point of X and Y. So this is just a two-dimensional rotation. So this is something you're familiar with. Then I want to stick in this gauge condition that I want to satisfy this combination to vanish. So that's the gauge condition I'd like to put in. But when you do so with a theta integral, what you have learned is that I need to accompany it together with this Jacobian. So that's the theta derivative in my case. So y cosine theta differentiated by theta is minus y sine theta. X sine theta differentiated by theta is x cosine theta. So this thing is a Jacobian. And we decided we need to take absolute value. And in this case, this can be 0 twice. So you get you satisfy the condition to be on this the gauge slice twice when you go around the circle, and they come with the opposite sign. So if you don't put this absolute value symbol here, you get 0. That's not what you want. But by putting in absolute value here, you get 2 instead. So that's the identity we can use. Namely, that if you have this integral, which we had on a previous slide, now I'm allowed to put in this identity into this integral. So here I have not changed anything. So if I perform this theta integral first, together with delta function in its absolute value of Jacobian, then I go back to the previous line. That's the original expression of the integral. So from here to there, I made sure nothing changes. And then I can choose my x and y integral, now rotated in such a fashion that the argument of this delta function is now the rotated y prime. So the argument of delta function is now y prime. So I rotate my xy integral over the plane to x prime y prime integral after rotation for a fixed theta. Then the delta function becomes delta y prime. That's what we wanted to stick in on the previous slide. But if I do so, then this piece, the Jacobian, also gets rotated to now x prime. And then I can perform this y prime integral. Then I end up dx prime integral e to the minus s times x prime absolute value. And x prime is a dummy variable, so I now switch back to x as my notation. So dx with x absolute value, together with this volume of the symmetry, namely rotational symmetry gives you 2 pi volume. But because each gauge slice passes through the point twice, I need to divide it by half. So that's the factor pi here. And as you see, that's exactly what we had here. Pi times absolute value of x together with the rest of the integral. Now this integral is gauge fixed in the sense that I no longer sum over all gauge slices. So this angular variable is redundant, and it's a waste of time to actually do this integral. So I don't have to do this anymore, but only at the expense of paying the price of this Jacobian factor, absolute value of x. And this we could derive by using this general method of understanding how delta function of a function works. So the morale of this is by using this kind of identity, by paying careful attention to the change of variable so that we can make sense of the delta function of a function, then your integral can be split in such a way that you have an integral over a chosen gauge slice times a volume that corresponds to the symmetry transformation you can perform on your system. So your integral now is split into the size of the symmetry itself times the gauge fixed integral after taking care of the symmetry, which now you fix with some gauge condition. So that's the idea of the Faddeev-Popov method, and we apply this idea to the gauge symmetry in 2 slides from now. So the next slide is yet another example of just not the rotational symmetry on the plane, but the 3-dimensional rotation symmetry, because that's when things become non-abelian and something pretty close to what we're supposed to do with the gauge symmetry. But anyway, before going there, are there any questions about this method?
just to be clear, is the
Go ahead.
This slide at the very top, it's claiming that it's about delta functions of a function, but
right.
This slide is just ordinary 1D
right.
calculus of functions.
Right.
So this
right.
is just supposed to be an analogy for now, and then we're about to do it with the function.
Right. So this is the function of function, but the argument of the function then becomes a field, something that depends on a field. So it ends up being a function of function of function. So we have to certainly generalize an idea to get there, but the basic principle is really just this.
Okay, just making sure that this was not supposed to be the delta function of a function yet.
Right,
wait.
right. So you're exactly right. So you'll see that in a moment. Any other questions here? Good. So anyway, so as you can see, this method looks kind of cumbersome, but the only purpose of this is to make sure that we don't make mistakes. So rather than sticking delta function of y by hand, which did lead to wrong result, we know how to stick in a delta function of y in a consistent fashion by making sure that this delta function comes together with the Jacobian so that the integral of that just changes, does not change the integral you're dealing with. So that's the only purpose of it. And for this purpose, you could have just switched to from the Cartesian coordinate to polar coordinate right away. You knew exactly what to do, so you didn't have to go through this. But if you go to more complicated examples, this actually really helps. So you're going to see that also in a moment. So how do we generalize this procedure? So if you have a function of variables, now it's multidimensional. And then, so this f of x is meant to be a gauge fixing condition. So what you can do is the following integral. So imagine you integrate over the symmetry, which could be some non-abelian symmetry, SON, SUN. And so this dg is meant to be an integration over the volume of all possible symmetry transformations. And this is a delta function of f of x, but x is now transformed by the symmetry. So this depends on where you are on this dg integral. And what we learned on the previous slide is that you can stick in the delta, the Jacobian df by dg. But now that it's multidimensional, Jacobian has to do with the determinant of this now matrix, because G is now multidimensional. And we learned that we are supposed to take the absolute value of determinant. And if you do so, that counts the number of zeros of this delta function. So that's what we learned basically from the previous example. Then we can put this identity into the original integral. So this is some n-dimensional integral over x, and r is just be some generalization of the distance from the origin on a previous example. But this may be something more complicated. But the whole point here is that S of r is supposed to be invariant under the symmetry transformation G. So this dnx integral is again redundant. We are summing the same thing over and over again. So we are trying to fix that. So having now this identity that this integral over G with this measure, integrand is supposed to return just a number. I stick this integral into this. So this dg delta function in a Jacobian is supposed to give you just a number of zeros, which is canceled by this the prefactor. So if I perform this EG integral first, then I'm guaranteed that I have not changed the result. Now, I change x to x prime, knowing that this measure is supposed to be invariant under the symmetry. This integrand also is invariant under symmetry. That's how we started out with by assumption. So I can switch from x integral to x prime integral. If I do so, this delta function of f of xg, now I'm basically saying xg to be x prime. So this now becomes f of x prime. So this delta function now forgets about G transformation. And this determinant, of course, used to be evaluated when this delta function, the argument delta function vanishes as a function of xg, but now it's also changed to this, the argument of delta function vanishes as a function of x prime. So it's evaluated where the argument f of x prime vanishes. But having done that, then the integrand, none of the species in integrand now knows about g. It's all eliminated because I have switched my integration variable from x to x prime. So everything now depends on x prime and doesn't depend on g anymore. So that's why I can perform the g integral because nothing depends on g. So this integral over dg now becomes the volume of the all possible symmetries in the system. And the rest is this. So again, x prime is a dummy variable for integral. So I switch my notation from x prime to x. Then I successfully have this gauge fixing condition of delta of f of x. So all factor, I don't care. And everything else is now this original x integral with the original integrand. But now I have stick in this delta function as my gauge fixing condition. So I don't need to sum over the same thing over and over again, only at the expense of sticking in this additional factor of the determinant of the change of variable. So if I do it this way, then I'm guaranteed not to change the result of the integral, but at the same time, I have successfully inserted this gauge fixing condition. So that's the Faddeev-Popov method. So I hope this is a straightforward generalization of what we have done with this very simple planar integral on the previous slides, but now it's generalized to multi-variables. Any questions on that? No? All right. So this is yet another example of integral, not path integral. So let's suppose you talk about the three-dimensional rotation. So the same idea, I have an integrand that depends only on the distance from the origin. So this integrand is invariant under three-dimensional rotation. So we'd like to fix the gauge for that. So the general three-dimensional rotation can be written by the order angles. And so what we like to do ideally to stick in the gauge fixing condition so that I integrate only along the z-axis. So sticking in delta x, delta y is the goal. So just like what we have learned on the previous slide, what you're supposed to do instead is stick in delta function of the x after the rotation or the symmetry transformation, so which I wrote by xo. So this is the rotated x, and this is rotated y. The goal is to integrate over z-axis. So if you start from z-axis, then rotation, x component after rotation, of course, comes to do with s times some certain angle. And so if you apply this rotation to 0, 0, z vector, then the first rotation doesn't do anything. So the only rotation that is relevant for the purpose is this rotation and that rotation. So when you do this rotation starting from the z-axis, then this is the component you pick up. So hence xo turns into z s13. So s13 is sine of theta 13. That's one of the Euler angles. And yo, if you work out the product of these rotation matrices, is z times cosine of theta 13 and sine of theta 23. So this is the argument of delta function now. So if you would like to compute the Jacobian factor, so the argument of the delta function is these two things. So the rotation takes care of the theta 23 rotation and theta 13 rotation. I just take the derivatives with respect to them. So this argument here depends only on theta 13. So I get this one and 0 for this row. And this one depends both on both angles. So theta 13 derivative will gives me this. Theta 23 derivative gives me this. So this is the matrix of the Jacobian. And I take the determinant, so that ends up being this factor here. So what I can do then is to stick in integration volume over all possible rotations times this determinant. And determinant we just worked out. And then I rotate x so that this new integration variable now points along the z direction. So the xo is now my x, yo is now my y. And so this thing actually turns into just z squared because along the z-axis, theta 13 vanishes, theta 23 vanishes. So this cosine factor just becomes 1. then nothing here now depends on this rotation, so this just turns into a volume over all possible rotations. Then I can perform x and y integrals so that this integration volume now turns into just the integral all along the z-axis. But I do have this Jacobian factor z squared. And you, of course, know from the beginning that this was supposed to be the right answer, because if you had switched to the spherical coordinates, d cube x turns into r squared dr times d omega. The omega is the solid angle, and omega integral is just 4 pi. I can forget about that. Then this integration volume turns into dr r squared times the function of r. And along the z-axis, of course, r is the same thing as z. So this is supposed to be the right answer. You knew this all along, but this is the way you can formalize the steps so that you make sure you don't get the wrong answer. So this is how I can have generalized this Faddeev-Popov method from the previous case that was analog of abelian gauge theory to now non-abelian gauge theory, which is, three-dimensional rotation is now non-abelian group. Okay, any questions about this? The next slide, I jump into gauge theory. Is everything okay? All right. So, so the general Faddeev-Popov method, therefore, is actually sticking this identity that the integral over the gauge volume can be done with a delta function and the determinant. So, in the case of the gauge theory, this f of x now turns into the gauge fixing condition, like del mu a mu is fixed to some function f of x. Okay, so that's the delta function I need to stick in. But what we have learned is that you need to look at this Jacobian by doing a symmetry transformation on the function. And we know how the symmetry transformation works on the gauge field. Infinitesimally, it's just given by this gradient times this commutator, which we can write in a compact notation as the covariant derivative acting on this the infinitesimal gauge variable omega. So how much this argument of the delta function changes is partial mu times covariant derivative acting on this gauge parameter omega. So that should be this determinant, namely that what I need to stick in is determinant of this derivative operator del mu d mu. Once I stick in this determinant, then we do not change the result of this path integral. So that's the straightforward
integral anywhere?
The integral is over the gauge volume, which I factored out already, Vg.
Well, I mean, like, when you had the identity for the delta function before, you were integrating over, like, all f, right? And now, like, there's no integral over, like, there's no path integral over df.
Oh, so we will actually do this next. So, okay. So this is the gauge fixed version of this integral. But now we need to recover what we have done in QED with having this gauge fixing term in the Lagrangian. So if everyone's happy with this step, then I move into the next step of integrating over this gauge fixing condition, little f. But is it okay for now? So the only new thing is this determinant. Go ahead.
You put the condition d mu a mu minus f is when that is 0, we activate the delta function. But aren't there more general conditions we could put on the gauge field? Like, for example, you can choose one of its components to vanish or something. And
that's right.
Like this.
Yeah, you can do that. So another gauge fixing condition that is used in literature is called axial gauge. So you choose, let's say, z component of A to vanish. You can do that. It turns out for that gauge fixing condition, then you look at the infinitesimal gauge variation. So change of AZ is del Z omega minus the commutator of AZ and omega. But you evaluate the determinant where the delta function, argument delta function vanishes. So AZ actually vanishes. So it turns out the gauge fixing condition is del Z omega. So you get determinant of del Z, which doesn't depend on gauge field. So for the axial gauge, it turns out the determinant of this the Jacobian doesn't depend on a gauge field. So it's an infinite constant, but nonetheless it's a constant. So you can factor that out. So you don't need to worry about this gauge fixing condition, it turns out. So axial gauge is a special gauge fixing condition where this determinant you don't need to pay attention to. But it comes with a price, namely that your gauge fixing condition is no longer Lorentz invariant. So it depends on your reference frame. It's actually useful for certain purposes. When you're looking for some scattering process, you can choose the axis to be along the direction of the particle that's emitted. And it turns out that actually gauge choice turns out to simplify some calculations, like generating this what's called a shower of the gluons emitted from this high energy particle. So there's some purpose of using the gauge fixing condition, but in general, you would like to retain the Lorentz invariance in actual calculations. So then the axial gauge turns out to be not a very convenient choice for that. So this is the only gauge condition which retains gauge invariance. Actually, I wouldn't say only. You can also put in a different gauge condition where the covariant derivative acting on A mu is certain function. And you can actually use that. Then determinant turns into covariant derivative. And that's yet another gauge fixing condition you can choose. The most sort of a standard gauge fixing condition is this one. So let me stick to that one. But you're completely right. You can have different gauge fixing conditions. But for each gauge fixing condition, then now you know what is the right determinant to be added to the integral, because now you know the mechanics of how to derive the correct change in the path integral without changing the result. And so for any gauge fixing condition you like, you can work out what determinant you're supposed to stick in, and then you can just go ahead and do actual calculations with it. So did I answer your question?
Yeah, thanks.
Okay, good. Any other questions? All right. So then we use yet another trick. So this choice of this function f of x was totally arbitrary, which corresponds to different gauge slices. So what would recover this Feynman gauge or Landau gauge we talked about in the case of QED is by smearing this gauge slice using this Gaussian weight. So this Gaussian weight is meant to be some kind of potential energy, which is minimized when f vanishes, namely when divergence A vanishes. But it's smeared. So if you go back to this picture of the many slices a couple of slides ago, then instead of sticking to one particular slice, you sort of average over nearby slices with this Gaussian weight. And so that's the function, the averaging we are doing here. And because we made sure the choice of this f of x doesn't affect my result, because the integrating over this gauge volume was meant to be just a number of zeros, and therefore it was an identity. So this integral, the path integral, doesn't depend on f. So smearing over f, again, is not supposed to change the result. Again, I'm using the fact that the over normalization factor coming from Gaussian integral, as long as it doesn't depend on the gauge field, it's just trivial normalization of the path integral, so I don't care about that. So by sticking in this 1 from this Gaussian integral, I stick in this df integral with this Gaussian weight. But then I can perform f integral, and then using this delta functional, f turns into del mu a mu, so that this Gaussian weight turns into the Gaussian weight of del mu a mu. So that's the gauge fixed Lagrangian we sort of secretly used in QED without Peskin-Schroeder telling you that that's what we have done. But now I have this freedom of a variable c, which I can choose arbitrarily. So I can choose c to be 1 for the Feynman gauge, c to be 0 for the Landau gauge. To avoid the singularity of c going to 0, I have yet another rewriting I do on the next slide. But this is the way this gauge fixing was supposed to be done. So instead of just sticking in this additional term to Lagrangian, I'm supposed to pay attention to this determinant. That's the main thing, which we were not aware of before. And as you can see, this whole process has to do with understanding how the geometry of the integral of the gauge field configurations would work. So if we didn't have this formulation based on path integral, I would assume that we would not have thought of this Faddeev-Popov method. So the advantage of path integral, which emphasized at the very beginning of this course, is to have this understanding that the quantization is also supposed to be just some kind of integral. And if we have this idea of the integral, we can actually understand the geometry of this integral. And knowing the geometry, we know how this determinant would arise just from the fact that you're sticking in this gauge slice condition, now with this additional smearing effect. So you know what you're supposed to do. So the path integral makes everything much more intuitive. And without the path integral formulation, we probably could not have actually figured out this is the right way to quantize the gauge theory. So I hope that addresses the question. I think that was from Andres. Okay, so does it answer your question?
It's kind of strange that you can smear the Gaussian like that, because I mean, I can always put in like a different sign in like the eye, and then you're just saying it gets absorbed into normalization.
Yeah, so this particular sign was chosen in such a way that this really allows us to invert the quadratic part of the Lagrangian to define a propagator. And you can sort of understand this why this sign is good, because if you remember, what is in the exponents e to the I Lagrangian, and the potential energy comes with negative v. So choosing this minus sign really makes this del mu a mu squared as a potential energy, which rises. So this is really the potential energy, which is positive definite, so that your path integral on average is fixed where the bottom of the potential is, namely where del mu a mu vanishes. So that makes this sign more intuitive, I think.
Okay,
And technical reason, of course, is to make sure that we can define the right propagator, but at least that argument makes the sign somewhat intuitive. Okay, any other questions about this?
Thank you.
Is it good? All right. So this is now the gauge fixed Lagrangian, and I do a little bit more rewriting so that we can actually understand this Lagrangian better, and we develop perturbation theory with it. So first of all, having this determinant is still not a good way of doing perturbation theory, because you have to compute determinant, stick that into path integral. So this is not the way you can understand the Feynman diagrams. So instead of sticking its determinant, I rewrite this determinant using a path integral over this fermion field C and C bar. So we talked about this already quite a while ago. So if you do the Gaussian integral over boson, you get determinant to negative 1/2 power. When you do the path integral of fermions, you get determinant, rather, not the inverse of it. So if you do perform the path integral of C and C bar, and that would reproduce this determinant. So that's the purpose of the C and C bar fields. In addition, I also did another rewriting of this gauge fixing term so that I'm allowed to safely take the limit of C going to 0. So instead of writing this del mu a mu squared, again, this is the Hubbard-Stratonovich transformation using this auxiliary field BA. So if I do B integral first, again with this Gaussian integral BA, then I complete the square with BA. So this becomes C times parentheses open, BA minus 1/c del mu a mu, parentheses close squared. With this remainder, that is precisely the term you wanted. So if you perform Gaussian integral of B first, then you recover this gauge fixing term we have introduced on a previous slide. But now this expression allows me to take the limit of C going to 0, and that's the Landau gauge. And it kind of makes sense. When C goes to 0, then this is the only term I have. And B integral is nothing but the B integral of e to the I b times function. So this reproduces the the delta function of del mu a mu, right? So the x integral e to the IPX gives you delta function of p. In the same way, B integral times this exponential factor gives you the delta function of del mu a mu. So that will be the Landau gauge. When C is 1, of course, that is the Feynman gauge, as we talked about before. So we did two rewriting here. One is to write this determinant as a path integral over C and C bar field. And we write this gauge fixing term. Now we're using this auxiliary field BA. So again, it's guaranteed that nothing has changed. So path integral is still supposed to yield the same result. Now, the strange thing though is the C and C bar are fermions, so that you get determinant, not inverse determinant. But C doesn't have a Lorentz index. So it's actually spin zero scalar field. So it's a Klein-Gordon field. So this is actually spin zero fermion field. And clearly that violates spin statistics theorem and therefore must be unphysical. And that's why the C and C bar fields are called Faddeev-Popov ghosts. So ghosts in the sense that you're not supposed to see them because they're unphysical. So that's why these fields are called ghosts. So clearly, these are unphysical degrees of freedom. But whenever you're dealing with gauge field, we are stuck with unphysical degrees of freedom anyway. So we talked about forward polarization of the gauge field, which was supposed to be unphysical. Backward polarization was also unphysical. And now we have two more unphysical things, C and C bar. So at least at this point, it looks like we made the problem worse. So the basic premise of all this discussion was to try to get rid of unphysical degrees of freedom and so to make sure that we make sense of the theory. But instead of getting rid of them, it looks like we have actually made the problem worse by introducing more unphysical degrees of freedom. But it turns out that this is exactly what we wanted, because having introduced two more unphysical degrees of freedom, C and C bar, these bad things cancel against each other. So I was stuck with two unphysical degrees of freedom within the description we had, namely that we want to describe two helicity states of the spin 1 massless particle, but we have 4-component A mu because it was forced on us by the Lorentz invariance. So we have 4 components to describe 2 degrees of freedom. That's why we had these two unphysical polarization states. But now that we have introduced 2 more unphysical degrees of freedom, it turns out that the way it works is 2 minus 2 is 0. So that's what I meant, bad things cancel against each other. So I will make this statement a little bit more rigorous on the next slide, but at least this rewriting of the Lagrangian makes sense. And the fact that C and C bar are ghosts also, I hope, makes sense. And then we try to see how we can reduce the theory down to only the physical degrees of freedom at the end of the day. Any questions about this?
Can you make C into a spinor?
No, we cannot. So this d mu, del mu, d mu, if you go back to where it came from the action on this gauge parameter. So this omega basically became C, namely that this derivative operator, del mu, d mu, is supposed to act on something like omega, which is a scalar function of space-time. So we cannot turn C into a spinor because this derivative operator was meant to act on a scalar function.
Thank you.
Okay. Any other questions?
What is the? I understand the need to introduce the ghost fermions, but why are we introducing the B boson auxiliary field?
So the B boson is needed only when we actually do the Landau gauge. So if you're sticking with the Feynman gauge, we don't need to do this.
Okay.
But at the same time, it turns out to be useful when we talk about the invariance of this gauge fixed Lagrangian, and that is what is called a BRST symmetry. So having this way of writing it actually makes things a little bit more transparent. So it's basically just for the convenience. There's no deep physical reason for it, but it's just convenient for the purpose of that discussion.
Okay.
Okay. Any other questions here?
One last question. Why did you choose a minus sign on the ghost fields?
Yeah, so there is also a purpose for it. So that choosing this minus sign guarantees that the propagator for C and C bar is the usual propagator for the scalar field, I over Q squared. Because when you actually do the integration by parts, and if you remove the gauge field part of this d mu, then this turns into just plus del mu c bar, del mu c. That's the usual sign for the kinetic term for the scalar field. So that's why I chose the negative sign.
Okay.
But it was, as you can see, it was arbitrary because unlike the usual scalar field, this C and C bar turns out to be independent fields. So if I change the sign of C bar, this measure doesn't change, but I can switch the sign to plus. So, I could have done it either way, because either way, I just get a determinant times an overall constant factor. So it doesn't matter at the end of the day. But again, this is chosen just for the matter of the later convenience. When I develop perturbation theory with it, we would like to use just the regular propagator of I over Q squared for the Faddeev-Popov pose, rather than minus I over Q squared. That's the only reason. Okay. Are you happy, Andres? Good.
Yeah.
Any other questions?
Yeah, I just have a quick question. I think you mentioned something like this, but I wanted to make sure this was the case. So that middle term in the exponential there, the BA times
this one?
Yeah, that guy. So that when you integrate over that and then you do the path integral, this is essentially the functional generalization of the exponential integral way of writing a delta function. Is that what that is, essentially?
That's right.
Okay.
Right. So that's exactly what you get in Landau gauge, where you don't have this quadratic piece.
Gotcha.
Okay.
Okay.
Right. Thank you, Nick. Any other questions here? Good. So we have learned what is the correct way of doing the gauge fixing. But as I said, what remains to be seen is that this way of doing gauge fixing really does eliminate these unphysical degrees of freedom. Now it looks like we made the problem worse, but it turns out this actually does eliminate unphysical degrees of freedom, so we need to see that. Okay, so here's the gauge fixing term, gauge fixed Lagrangian. So S is the original Lagrangian we had, which is manifestly gauge invariant, F mu nu, psi bar del mu, gamma mu del mu minus M psi. And then in addition, we have these additional pieces coming from gauge fixing. So to make the things a little bit more explicit, so the C originates from this gauge fixing, so the gauge transformation parameter omega. So omega was a matrix, omega ATA. So as a result, this C field is also meant to be a matrix, so summed over these generators TA, and so is C bar. So what's meant by this kinetic term of C and C bar is actually a matrix, so we need to understand what exactly that means. In addition, despite the notation, the C is actually real, and C bar is not a complex conjugate of it, and C bar is actually purely imaginary. And the Peskin-Struder don't mention this. And this I learned only by looking at this paper by Kugo and Ojima. And this is one of the standard references for the BRST formalism in a canonical quantization. We will look at that in a moment. So C is actually real. C bar is pure imaginary. And so in terms of C and C bar field, if you write out this the Lagrangian term explicitly, it's meant to be this. And I realized I made a sign mistake here, so it's a typo. So d mu C, the covariant derivative acts on C, is supposed to be this, which can be written in a compact notation, d mu acting on C. So the first one is just a partial derivative. And second one comes from the commutator of A mu and C that can be written in terms of the structure constant FABC. So this d mu C is meant by this. Oh, no, I didn't make a sign mistake. So I did an integration with parts. So this partial derivative now acting on C bar. So that's why I have this one here. And if you use a matrix notation, then TATB trace is half delta AB. So I need to compensate a factor of half by factoring 2 here. So I can also write this, the Faddeev-Popov Lagrangian as 2 times trace of del mu C bar matrix times this commutator matrix d mu and C. So this is just a simple rewriting of the Lagrangian. And now having this explicit form, I can see why taking C to be real and C bar to imaginary makes sense. So here is the Lagrangian. I take the Hermitian conjugate of it. And of course, Lagrangian is supposed to be Hermitian. So this shouldn't change after the Hermitian conjugation. And if I do that, then this d mu C conjugate comes first, and C bar conjugate comes next, because conjugation changes the order of the matrices or operators. So this del mu d mu acting on C comes first, and because C is real, it doesn't change the sign. C bar conjugate comes next, but C bar is meant to be anti-Hermitian or imaginary. There's an additional minus sign here. And then we remember the fact that these are meant to be fermions. So if you interchange the order of the fermion fields, they are Grassmann odd, so they anti-commute. So changing order between C and C bar gives you a minus sign. That cancels one of the minus signs here. The other minus sign remains. So that's how this Lagrangian is Hermitian. So if I have not taken the fact that C is Hermitian and C bar is anti-Hermitian, I wouldn't have seen the Lagrangian is real. And knowing this property of C and C bar, now I can see the Lagrangian is Hermitian. So this sounds kind of crazy at the first, but you know, everything actually is consistent once you make this assignment that C is real, C bar is imaginary. And this Lagrangian also has a new symmetry called ghost number conservation. So because C is real, C bar is imaginary, I'm not allowed to change the phase of C and C bar, but I'm allowed to change the normalization of C and C bar in opposite way. So eta is a real parameter. So C changes to e to the eta C, C bar changes to e to the negative eta C bar, and because e to the eta, e minus eta are just numbers, they cancel between C and C bar in the Lagrangian. So this is a symmetry, which leads to a certain conservation law, which is a conservation law of the ghost number. So it turns out that your Hilbert space can be decomposed into a fixed ghost number state, and that actually turns out to be useful later on. But finally, this is the most important thing. So even after gauge fixing, there could be a residual gauge symmetry. And that's what we have seen in Lorentz gauge in QED. So you employ this gauge fixing condition, del mu A mu vanishing. And suppose you do a additional gauge change, A mu minus del mu theta. But if del mu theta vanishes, namely if theta is solution to the Master-Klein-Gordon equation, then it doesn't change the gauge fixing condition. So even after choosing Lorentz gauge, there is still a residual gauge symmetry. So there's still limited choice of the gauge transformations you're allowed to do, even after the gauge fixing condition. So what we have done here is sort of analog of the Lorentz gauge for the generalized non-abelian gauge theory. One can ask the question, what is this residual gauge symmetry of this Lagrangian? So that's something which turns out to be precisely what the BSST transformation is about. And that allows us to understand how the unphysical degrees of freedom in the end would not appear in any physical processes. Okay, this is sort of just a little bit of a formalism, but any questions about this? Okay, so we need to understand this residual gauge symmetry. So here is the answer. So this change of the gauge field and various other fields is an invariance of the Lagrangian, even including this gauge fixing condition. And of course, you can just go ahead and check this invariance by explicit calculation, but for the later purpose, it's actually useful to go through the following set of arguments. First of all, this main action depends only on the gauge field and matter fields, doesn't depend on these ghost fields and auxiliary field. So you can see why this one doesn't change, because this transformation with parameter epsilon is nothing but the gauge transformation, because if I regard epsilon times c to be omega, that's the gauge, the parameter, which comes into this gauge transformation e to the I omega, I forgot a factor I here, I'm sorry, then this is nothing but the infinitesimal gauge transformation on gauge fields and matter fields. So once you know that this epsilon c can be regarded as the gauge parameter of the usual gauge transformation, it's guaranteed that S part of the Lagrangian doesn't change because it's gauge invariant. What is non-trivial is the fact that the rest of the Lagrangian doesn't change either. And because this is a gauge fixed Lagrangian, usual gauge transformation is supposed to change it, but this gauge transformation doesn't, and that's why this is meant to be the residual gauge symmetry after the gauge fixing. And the strange thing about transformation, though, is this parameter epsilon is actually fermionic parameter, because epsilon times c is what corresponds to the usual gauge transformation function omega, which is bosonic. So epsilon is actually a fermionic parameter. So we are talking about some kind of fermionic symmetry, which we haven't seen before, but now we're facing it. And so this is what I just said. It's just a limited set of gauge transformation. This is the subgroup of gauge symmetry. Therefore, it's guaranteed not to change S. But the rest is non-trivial. And the way we can see why this doesn't change the gauge invariance goes through the argument of what is called a nilpotency. Namely that this new symmetry we're talking about, if you do it twice, you get trivially zero, and that's the meaning of nilpotency. So what we would like to do is that take this transformation, we first verify that this is nilpotent, and that actually allows us to verify the invariance of Lagrangian in a very transparent way. And the nilpotency is kind of obvious for the last two. So transformation of B is already zero. If you do it once again, of course it's zero. So that's obvious. Transformation C bar is B, but its transformation is zero. So if you do symmetry transformation twice on C bar, that vanishes. So the nilpotency is obvious for the last two, but it may not be obvious for the first three. So that's something we need to verify. And in order to make sure that this epsilon c is a Hermitian gauge parameter, epsilon turns out to be anti-Hermitian. So if I take complex conjugate of epsilon c, that turns into c dagger epsilon dagger. C dagger, we learned, is c itself. So epsilon dagger should be minus epsilon, so that if I change the order between epsilon c, that goes back to the original omega. So anti-Hermitian, epsilon is supposed to be anti-Hermitian. And that makes sense because B is an auxiliary real field. Epsilon times B then is anti-Hermitian. That's exactly what we learned, that C bar is supposed to be anti-Hermitian. So this assignment of C being Hermitian and C bar being anti-Hermitian is actually crucial for the rest of the consistency of the arguments. But anyway, so this is the set of transformation properties we need to look at. Any questions about this?
So I wonder if the C squared factor is a typo in delta epsilon c, because C squared is zero. Right?
No, C squared is not zero. And so C squared, remember C is CATA. So it's a matrix.
Oh, okay, sorry.
If I square this, then there is a piece which corresponds to the anti-symmetric product of TA and TB, which is nothing but a commutator. So C squared turns out to be structure constant FABC times CDCC. So 2C is antisymmetric, but structure constant is also antisymmetric. So this is actually non-vanishing.
Thank you.
So that's an excellent question, and we rely on that fact for the rest of the arguments. Thank you, Chao. Anything else?
Are we meant to interpret B and C bar, for example, in the fourth one, as having implicit indices for the generators, or?
Yeah, so this C and C bar and B are all matrices. So yeah. BA summed over together with TA. So B is now a matrix. Yeah, thanks for asking the question. And besides the column vector, A mu is also a matrix. So, everything is now generalized to matrices. Okay, I'm running out of time. So let me just flash the next slide, and we will start from there on Thursday. And by the way, so this new symmetry is meant to be quote-unquote global symmetry because the parameter of the symmetry, namely epsilon, is a space-time constant. It's no longer a function of space and time. It's meant to be a space-time constant. So what I actually do on Thursday is that we understand nilpotency of the on every field. So we do the BRST transformation C twice, then you can show that vanishes. We do the BRST transformation on the matter field side twice. Again, we can verify that vanishes. We can do that also on the gauge field twice, that also vanishes. So it's nilpotent. And after the end of the day, you can also verify that this entire gauge fixing Lagrangian can be written as a BRST transformation of this combination. And having learned that, then this is the proof why this Lagrangian is invariant, because if the Lagrangian is written as a BRST transformation of something, we have learned that doing twice gives you identically zero, namely that BRST transformation of the gauge fixing term is supposed to be zero, and therefore that's an invariance. So that's how we can show that this whole Lagrangian still has this residual gauge transformation. And knowing that, then we can talk about how then the physical polarization would appear at the end of the day. And so that's what we would like to discuss on Thursday. Okay, so we will repeat this discussion on Thursday again. So no, don't worry about missing something here. But anyway, so that's the use of this BRST transformation, and that in the end would allow us to verify that unphysical degrees of freedom would disappear from any physical processes. Okay, questions?
So wait, that last action is very complicated. Where did you even find those BRC transformations to begin with? Did you like just stare at it long enough that it popped up, or is there?
Yeah, you know, I confess, if I were to solve this problem myself, I may not have figured this out, right? It looks complicated, but it turns out that it sort of makes sense once you understand that epsilon c is the gauge parameter. So C is a matrix. The transform is a matrix. So that's a commutator of this gauge parameter in C, and that's sort of exactly what you get here. And the transformation C bar is the only thing that is a little non-trivial, but it turns out once you accept this, this works for any gauge fixing condition. So this turns out to be completely general. Whatever gauge fixing you do, then you find BA of the gauge fixing condition here. Then it turns out that if you write it in the expression I wrote down at the very end. So this is always true, namely that this C bar BA plus C bar A times gauge fixing condition is always the gauge fixed Lagrangian, and therefore it's guaranteed to be BRST invariant. So once you know this trick, everything becomes transparent, but to figure this out for the first time, it looks very non-trivial. That's why we pay homage to Becky, Ruet, Storer, and Tutlin as a symmetry according to the people who discovered it. And so I confess, it's not something I would have probably guessed from the first sight.
Okay, thank you.
All right. Any other questions?
Yeah, so I wanted to come back to Mario's earlier question about how in classical electrodynamics you have an entire gauge field, and here we ended up with a single number. So is the idea that this single number parameter that's defining our gauge, there's really no classical it seems to me like we're singling out Lorentz gauge, and then that single number parameter that we're left with is just describing how much, so I guess how much we're going into these parallel directions, how much we're allowing ourselves to include those in our sum. So is there no real classical analog of, I guess, like
so
Feynman gauge or?
Right. So classical analog is really being confined on one of these slices, right? So that's the Lorentz gauge condition. But having this parameter C, you can average very steeply along the slice or very broadly among many slices. And that's the choice you're making. And either way, on average, del mu A mu vanishes, but how much you smear is the parameter we're introducing. And of course, we're trying to fix the gauge. So the Landau gauge really does fix you to only one of the slices. So that's something you can do. But for the practical purposes, dealing with this factor of G mu nu minus Q mu nu over Q squared is cumbersome. It's much easier to have just G mu nu over Q squared. That's the property I used in on the previous last semester. And that does correspond to a certain level of smearing over these different gauge slices. And you are allowed to do it. And because that's the easiest, we do it. So there's no deep reason other than that.
Okay. So Lorentz gauge is taking a central role in everything we're doing here. And
to maintain Lorentz invariance, yep.
And Landau gauge is kind of the closest thing to, or is essentially just Lorentz gauge. Okay, cool.
Okay. Any other questions? Okay, good. So we do have office hour from 5 o'clock today. So please join in. And if you have additional questions on the material today, please ask. And I'm going to post the slides on the B courses soon, so you can actually look through it yourself and see if you have any further questions. Okay. See you later.
Thanks. Goodbye.
Thank you.
Bye. Stay safe.